is a full day. So, because it makes more sense to have the review class prior to the test rather than two classes prior. Review class is scheduled for Thursday, the test is scheduled for Monday. We don't have sufficient time to have two review classes, which means today we're gonna press on into chapter 4. Obviously, nothing we do in a chapter 4 section is gonna be on a chapter 3 test. And I think without too much difficulty, we can get through all of section 4.1, because for the most part, it is probably closer to any other section we're gonna do this year, a review of Science 10. It's just writing and balancing chemical formulas, or chemical equations. So, Sherry writes it as if you have never done any chemical balancing before. Even though she knows you have, it's simply if you forgot what you did in grade 10, or you maybe didn't master it in the first place. The section is written from a basic enough level that by the end of it, you shouldn't really have any trouble with balancing. As I've said several times, I didn't teach most of you last year, so I don't know who had no trouble or who did have trouble. But I think based on the ones we do today and some of the tips or hints Sherry gave us, which if I taught you Science 10, you already have them, you should be in pretty good shape. To introduce the idea of writing and balancing chemical equations, she gives us the example of the electrolysis of water. Electrolysis stands for electrochemical lysis. How many of you were in Life Sciences 11? So you've talked about the lytic cycle of, for example, a T4 bacteriophage. So why do we call it a lytic cycle? What does that word mean? Didn't that, didn't you ever wonder about why do we call it that? You know what the word lysis means? Break apart. That's why we call it a lytic cycle. Part of the cycle, that bacterium that's been invaded bursts, releases a whole bunch of more virus particles, correct? That's why we call it that. So this means electrochemical lysis. We're using electric current to pull apart a compound. That's what it is, okay? For this to work, water has to conduct electricity. Water doesn't conduct electricity well because there's hardly any ions in it. So when she says ionized water, you might wonder what that is. What is that? Water's a covalent compound. We'll learn in Chem 12 that there's a tiny amount of hydrogen and hydroxide ions in it, but not enough to sustain conductivity. So what we do is we add something to water that allows for mobile charges to exist, which is what we mean when current is conducted. It's just that those charge couriers don't take part in the chemical change. So what we often throw in is a little bit of potassium sulfate. The potassium ions are the positive couriers of charge. The sulfate anions are the negative couriers of charge, and they have to move. So what happens is the potassium ions are attracted to the negative electrode, but when they get there, nothing chemically happens to them. Rather, at the negative electrode, the hydrogen in the water is released as hydrogen gas. At the other electrode, the positive electrode, the sulfate anions go there, so they carry charge to that electrode. It's just that when they get there, they don't do anything either. What happens is the oxygen in the water is released as oxygen gas. What Sherry wants you to do here is eventually end up with a balanced formula equation. So, in short, there's water, it's a liquid at room temperature. It's the only reactant. And you know from Science 10 that if we only have one reactant, we call this a decomposition reaction. This is a binary compound. If we're decomposing a binary compound, we get two elements. Each of the elements we get are diatomic, and they exist as gases in their elemental form. So that's often what we refer to as a skeletal equation. It's the formulas, the identity of the reactants and products, but not necessarily the balanced equation. Sometimes, if the formulas are correct, it's already balanced, but in this case it isn't. We've got two oxygens here, we've only got one here. So if we balance it, we've got to put a 2 there, and then a 2 there, okay? Now, remember Avogadro's hypothesis from chapter 3. That is something you need to remember. Any of you guys remember that hypothesis? Avogadro effectively interpreted Joseph Louis Gay-Lussac's findings, who said that gases always react in whole number volume ratios. So Avogadro thought, well, maybe the volume has something to do with the number of particles that are in that volume. And his hypothesis said that equal volumes of gases at the same temperature and pressure contain the same number of particles. If we assume that the hydrogen and the oxygen are at the same temperature and pressure, if we get twice the number of hydrogen, we should get twice the volume of hydrogen. So if you look at the diagram, we know which one's hydrogen, because we're producing twice as many hydrogen molecules as oxygen molecules, which has to mean we're also producing twice the volume of oxygen. And if you look at how vigorous the bubbles appear at each of the electrodes, the one that has the bubbles coming off the fastest is the hydrogen electrode. And Sherry says here, include anything else you feel is necessary to help your equation fully describe what is happening. I think probably what she means there is we'll often put that over an arrow. Sometimes over or and or under the arrow we might put the catalyst or conditions like heat, for example. DC means direct current. So we're running current through the liquid, and because there are mobile ions in it, current's conducting. Chemistry is the study of matter and its changes. You've already learned how physical and chemical changes differ. Chemical changes always produce new substances with new properties because we break and form chemical bonds. Process of photosynthesis, aerobic cellular respiration, for example, involves a series of chemical reactions that both produce, in the case of photosynthesis, and use, in the case of respiration, oxygen. These reactions are taking place right now in our bodies. Well, that's not taking place in our bodies, but this is. Photosynthesis and respiration occur in plants, but only photosynthesis happens in plants, okay, not in animals. And notice she says these reactions are taking place right now in our bodies and in most of the living things in our world. So plants respire, animals respire. Do you know of any type of organism in which that doesn't occur? This is also directed at the life sciences folk. Is there anything living that, as far as you know, doesn't undergo aerobic respiration? You talk about bacteria at all? You ever heard of anaerobic bacteria? What does anaerobic mean? Without oxygen. So there are bacteria that live in the absence of oxygen. Do you know any famous bacteria that live in the absence of oxygen? Anaerobic respiration. You guys heard of that? Anaerobic, without oxygen. Any of your parents get Botox? You know what the neurotoxin is? It's produced by an anaerobic bacteria called Clostridium botulinum. And if you ever buy a canned food and the can is bulging, do not open it, do not eat it, because it could very well mean that there's botulism in there. And that toxin, that neurotoxin, is one of the most toxic substances known. Even though it's natural, it's scary deadly. So when a doctor injects Botox into the wrinkles in your eyes or wherever, what that is doing is it's basically turning the nerves off. It's a neurotoxin. And that's why apparently the wrinkles go away. I've never had it, but it's a very dangerous substance. And that's an anaerobic bacteria. It doesn't need oxygen. Anyway, I digress. Most people take chemical reactions for granted. And I don't understand this last part, as if they were magic. If it's magic, you're not likely to take it for granted. I think people do take chemistry for granted because you can't see it. You can't see most of the results of the chemical reactions that are around you. Plants grow slowly. You grow slowly. But you don't see the hundreds of reactions happening in your body every second. You just take advantage of them. You stay alive. Okay? This section is about expressing those chemical changes. When you email or text message your friends, you probably use abbreviations or text speed to make it easier to communicate. In math, equations are often used to communicate operations involving numbers. Chemists use chemical equations to condense a large amount of information into a short expression. And there's a whole bunch of stuff that isn't available from this balanced equation. This is just how much of what you start with and how much of what it turns into. But the individual steps getting from here to here, you never see that in a chemical equation. That's something we talk about in Chem 12, called a reaction mechanism, a series of steps that get us from reactants to product. So in a lot of cases, the balanced formula equation is just a summary, all right? In 1774, Joseph Priestley performed a famous chemical reaction that led to the discovery of oxygen. His synthesis involved now, she's called it a synthesis. I think she's just referring to the chemical reaction because this isn't a synthesis, it's actually a decomposition. And it's a interesting demo to do. It has to be done under a fume hood because mercury vapor is very dangerous. But you turn a red-orange powder. When you heat it in a test tube, it turns into a silvery liquid and you generate a gas. Now, Priestley didn't know what he had discovered. What he did notice, though, is if he collected that gas and directed it at a hamster in a cage, the hamster seemed to run faster on the wheel. So his first label of this gas was called lively air. Sherry gives you a diagram of that particular reaction. And she said, you can tell that a chemical reaction has occurred by looking for evidence of chemical change. Remember the definition of a chemical change that I gave you earlier in the year. Any change in which experimental evidence indicates that original substances, reactants have been consumed and new substances, products have been produced. Noticeable absorption or release of heat. Now, it could be heat, it could be light, it could be other forms of energy. It could be sound, it could be kinetic energy. So there's lots of different types of energy released. And noticeable means compared to physical changes. Because physical changes are also exo or endo. They just, the amount of energy is tiny compared to chemical changes. Color change, absolutely. I would have put here in the absence of boiling. Because when you boil water, you see bubbles, but that's not a chemical change. So formation of bubbles or release of bubbles in the absence of boiling, and then a formation of precipitate. I think we may have added relatively difficult to reverse. But these are for, any one of these things is evidence of a chemical change. Not uncommon to have, several of these happening in the same reaction vessel, but all you need is one. Historical evidence connects Priestley's experiments with oxygen with another famous chemist, Antoine Lavoisier. They lived about the same time. Priestley was in England, Lavoisier was in France. Lavoisier's experiments were more quantitative. Lavoisier was meticulous, almost obsessed with keeping accurate records of the masses of his reactants before and the masses of his products afterwards. Lavoisier liked to measure volumes and masses of the chemicals he studied. Lavoisier is generally credited with formulating the law of conservation of mass. It simply states that the mass before and after a chemical reaction remains constant. Or put another way, matter is neither created nor destroyed during the chemical change. Priestley and Lavoisier were both radical thinkers for the time they lived in. Englishman Priestley supported the French revolutionists, led to his persecution, and eventually had to flee from Europe altogether. He lived the last of his days in Pennsylvania, United States. Lavoisier's problems were even more severe as he eventually lost his head to the guillotine at the height of the French Revolution. In almost all of the experiments Lavoisier did, in the data he gathered, his wife was a big part of that. She helped him interpret some of the data, she helped him set up the experiments, she helped write up the results of the experiments, but to my knowledge, he never gave her any credit for her contribution to his work. He was also very fond of ridiculing his contemporaries in public. And one of the guys that he was fond of ridiculing, basically, I'm smarter than you are, and here's evidence, was an individual who held a little bit of sway with the mobs during the French Revolution. And that guy was instrumental in getting poor Antoine's head cut off. So it's kind of a karma thing, all right? So brilliant chemist, sometimes he's called the father of modern chemistry. He's not maybe someone you'd want to be best friends with. If you look at the equation for the decomposition of mercury oxide, you'll notice that clearly we don't have enough oxygen on the left-hand side. And again, she's coming at this from the perspective that you know nothing about balancing. To obey the law of conservation of mass, we have to make sure that the same number of each atom appears on the reactant and the product side. Whether you imagine a scale or not, it's clear we only got one oxygen here, two here. So it looks like we've created mass, which we can't do. The only way to balance an equation, as you know, is to change coefficients. With no coefficients there, it's assumed they're all one. But the only way I can get two oxygens on the left-hand side is to put a 2 here. I can't change subscripts. That changes the chemical identity of the compound. Indeed, it may make a compound that doesn't even exist. So never change subscripts, only change coefficients. By putting a 2 there, I balance oxygen, but I unbalance mercury, so then I have a 2 there. And there isn't a simpler example of a balancing equation. And Sherry says it's not a bad idea at the end to check that you do have the same number of each atom of each element. Not necessary for this, you can tell by looking at it. But it is a good idea when we're doing balancing an equation where it may have taken you a bunch of steps, and maybe there's a whole bunch of different compounds, and maybe those compounds are big, or there's a big number of coefficients, and we'll see some examples of that before the end of today. If I taught you Chem 11 last year, then you probably got this as a handout. These are hints in balancing an equation. The only equations you'll be asked to balance in grade 11 Chem are ones that can be balanced by inspection, meaning you don't need a complicated stepwise process. In Chem 12 you do. Some of the equations you have to balance in Chem 12 this won't work. It's given enough time it might, but some of those equations are like really big coefficients, really complicated. But this works for everything you'll need to do in Chem 11. If I was gonna pick the one to start with, I probably would have done this. You might get formulas, and then you just have to balance the formula equation. But you might also just get the names of the reactants and products. So if you're writing the formulas, as she says, make certain all of the formulas are correct. A small mistake means any time you spend trying to balance that will be a waste of time. Because even if you can balance it, it'll be wrong because the formula is wrong. It also may be impossible to balance. So it's never a waste of time to make sure before you start balancing that those formulas you wrote are correct. And you can be quite sure that in the chapter 4 test there will be writing and balancing equations. Then we go back to the top. Begin by balancing atoms that appear in only one place on each side of the equation. Atoms that appear in too many places will be more difficult to balance. Should always be left until the end. That's often true with oxygen and hydrogen, more so for oxygen, but if you see something in one compound on the left but two on the right, wait till the end to do it. Balance atoms that occur in elemental form, present as just free elements, do them last. The point there is no coefficient you put in front of an element will screw anything else that you did for something in a compound, because it's all by itself. Remember that some chemicals, some elements exist as polyatomic species. So all of the halogens plus hydrogen, oxygen, nitrogen, when they're by themselves, there's a 2 there. Phosphorus is P4. It's an interesting little molecule. If you look at your periodic table, how many electrons does phosphorus need to be like the nearest noble gas? 3. So you'd say, okay, well, if phosphorus exists as P4, how could every phosphorus in there get the benefit of 3 more electrons? Well, the structure is kind of interesting. It's kind of like a pyramid. And if you look at any phosphorus in there, it's stuck to 3 others. This one's stuck to 1, 2, 3. This one is 1, 2, 3. This one is 1, 2, 3. So by putting 4 of them together, each are stuck to 3 other atoms. That's where they get those 3 extra electrons from. Metals are never polyatomic. So there's never a 2 or a 3 or a 4 under a metal. Metal atoms are just 1 atom, okay? If polyatomic ions stay together, balance them together. So for example, if you got phosphate on the left and phosphate on the right, leave all the atoms together. Don't, if it's functioning as a unit, balance it as a unit. Once a coefficient has been placed in front of a molecule or formula unit, finish balancing the rest of the atoms in that species before moving on, unless, of course, you've got an atom that's in multiple places. It's always a good idea to perform a check, such as one at table 4 and 1, particularly when you have longer, more difficult equations. So, if Mr. Dawson taught you Science 10, he may have given you that as well. I photocopied that, because that is the best succinct summary of how to balance by inspection that I've seen. And it works for everything we're going to do today. Here's introductory, which basically means, unless you're in a coma, you should have no problem with this. So what she puts down the left-hand side is incorporating those hints. Notice that barium and aluminum are present as elements. You having trouble staying awake? You should drink more coffee. So we're going to do barium and aluminum last. Second thing we notice is that nitrate stays together. So because we're going to do barium and aluminum last, and because the only other species is nitrate, let's start with nitrate. We got 3 nitrate on this side, we got 2 here. Least common multiple of 2 is 3 is 6. So if we put a 3 there and a 2 there, we got 6 nitrate on each side, right? Nothing to it. Now we're gonna do the barium and aluminum. 3 barium, 3 barium, there's nothing else stuck to that, so it's not gonna screw anything else up. 2 aluminum, 2 aluminum. And by the way, what type of reaction is that?
Synthesis.
Single replacement. That's what section 4.2 is about, classifying reactions. Although, whereas section 4.1 is a review of science 10, and not much beyond that, section 4.2, each of the reaction types we talk about, we're gonna do synthesis, decomposition, single and double replacement, combustion, neutralization. Each of the ones we talk about, we're gonna add more to it than for each type than we did in grade 10, okay? Now that's, again, you're conscious, ergo you should be able to do that. This one's a little tricky. Notice that we have a polyatomic ion on the right, but it's not the same polyatomic ion on the left. So there's no chromate on the left. We got hydroxide on the left, but there's no hydroxide on the right. So we can't use the polyatomic ion thing staying together. A good place to start would therefore be, what atom are we not going to start with? Which element are we not going to start with?
Oxygen.
Oxygen, because it's present everywhere. Moreover, we're going to leave it till the end, so we don't start with it because it's in everything. But we're going to end with it because it's an element. In other words, that's the last thing we're going to do to balance, okay? Sodium is present in one place on the left and the right, chromium is, hydrogen is. So let's balance the ones that are present in one place on both sides first. If we go to sodium here, there's 1 sodium here. This is the only compound sodium's in, there's 2 of them here. So to balance sodium, that's the only thing we can do, right? Now, it might be tempting to say, okay, let's do the oxygen. But remember, we're gonna leave it till the end. Let's now go to the hydrogen. 2 of these means we got 2 hydrogens, we got 2 hydrogens, so hydrogen's done. Now we'll do chromium. We got 1 chromium on the right. This is the only compound chromium's in, but we got 2 on the left. So the only thing we can do to balance chromium is to put a 2 in front of the compound that chromium's in. And Sherry tells us the benefit of using a pencil and eraser becomes immediately evident, because now we gotta go back and fix the sodium. So 4 sodium here, 4 sodium there. 4 hydrogen here, 4 hydrogen there. Okay? So now everything except oxygen is balanced. 4 sodium, 4 hydrogen, 2 chromium. Now we'll count the oxygens. On this side, we have 4 and 3 is 7, 8, 9. So we've got 9 oxygens on this side. On this side, we've got 2 times 4 is 8, plus 2 is 10. So we need 1 more oxygen. We're not gonna touch either of these, because anything we do with those is gonna group up sodium or hydrogen and chromium. So we need 10 oxygens on this side. We have 9. Well, if we write 1.5, it's balanced now, isn't it? 1.5 times 2 is 3. 3 plus 3 is 6, and 4 is 10. So it's balanced now, isn't it? Everybody agree with that? 1.5 times 2 is 3. We can't leave it as a half, because fractions of molecules don't react. A correctly balanced equation has to have the smallest integral coefficients in front of it. All we do now, if it is balanced, if we do the same thing to the left-hand side as the right-hand side, it'll still be balanced, just like an algebraic equation. So multiply everything by 2. When I do that, instead of 4 of these, I have 8. Instead of one of these, I have 2. Instead of 1.5 of those, I have 3. Instead of 2 of those, I've got 4. And instead of 2 of those, I've got 4. Let's make sure that I got the same number of each atom. I got 8 sodium, 8 hydrogen, 4 chromium, 8 and 3 is 14. 8 and 6 is 14. 14 and 6 is 20. 4 times 4 is 16, plus 4 is 20. And also confirm that the coefficients are the smallest whole numbers, and they are. So really, the only bullet that we took advantage of is leave the oxygen till the end and balance the elements that appear in one place on the left and the right. That's all we did. And because we left this at the end, we didn't screw anything else up. Does that make sense? Well, let's have a look at some practice problems. What she's asked you to do here, after she eventually gets to the balanced equation, is confirm for each of the 4 elements that we do have the same number of each on both sides. 2A is just like your first sample problem. Straight double replace or single replacement. We would start by balancing the sulfate, then the aluminum, then the hydrogen, nothing to it. But let's do C. That's, you could call that the combustion of ammonia. By exactly the same argument, which are we not going to start with for C? Oxygen. We're not only not going to start with it, we're going to end with it because it's an element. So nitrogen's present in one place to the left and right, hydrogen is, so we'll do those first. We got 1 nitrogen here, we got 1 there, nitrogen's done. We got 3 hydrogen here and 2 there, least common multiple of 3 and 2 is 6. So if I put a 3 here and a 2 there, that balances the hydrogen, but it unbalances nitrogen. So I gotta go back and put a 2 here. Now we'll do oxygen. I've got 2 and 3 is 5. 2 doesn't go evenly into 5, but based on what we had to do in the last example, what do I put in there to temporarily balance it? 2.5, right? Now I just multiply everything by 2. So I get 4 ammonia, 5 oxygen, 6 water, and 4 nitrogen monoxide. Okay. Now B is a little tricky too, but for B, what I would do, I might write the water instead of H, I'd write it as HOH. And then you can imagine that OH is that OH. This is actually double replacement. But I'm not going to do them all for you. Notice that everything we've done up till now, the formulas have been given. But they're not always given. And the next step, obviously, would be, well, what if you're just given the names? So that's the other level of complexity. This is the last set of practice problems in this section. So let's do some unbalanced or formula or skeletal formula equations in the review, and then we'll do maybe a written response or a word equation. There's more than one of these we can do. Let's start with, what about O? Do O for me. And to the extent you're able, pretend you're writing a test. I would suggest that the first question you might want to ask yourself is, what element am I not going to start with? Use pencil and an eraser.
Fuck out. Holy whiff. I got that one. I got it. You guys suck at throwing.
Dude, it's like flimsy, bro.
You gotta flick it like a card.
I'm not trying to deck somebody in the head, man.
This looks hard initially, but don't look at an equation and convince yourself it's hard. It might be unfamiliar to you, but just use the hints. If the first thing you do is realize you're gonna leave fluorine till the end, that's almost the entire battle, okay? Notice that every element except fluorine is in one place on the left and in one place on the right. So just do those, and the fluorine will take care of itself. Done? One lithium, one aluminum, 4 hydrogen, 6 hydrogen. Least common multiple of 6 and 4 is 12, right? So as we put a 2 there and a 3 there, hydrogen's balancing, right? We're not doing fluorine until the end. 3 lithium, 3 aluminum, 3 aluminum. Now we can do boron. We got 4 boron here. We got 4 boron there. Everything now except fluorine is balanced, right? Except fluorine is balanced. We've got now 3 times 3 is 9 plus 3 is 12.
4, 3, 3, 2.
Oh, shit.
We've got 12 here, 3 lithium, 3 aluminum, 12 hydrogen, 3 lithium, 3 aluminum, 12 hydrogen, 4 boron, done. And by the way, if we ended up having to put coefficients in front of everything, the fluorine better be balanced, because we got nothing else to play with, right? Now, there might be 1 or 2 more we want to look at. If we were going to look at N, which are we not going to do first? I would say hydrogen, because we got hydrogen in one place on the left, but 2 places on the right. Nitrogen's in one place on the left and the right. Bromine is on one place on the left and the right. Barium and oxygen are in one place on the left and the right. So if we do those and leave the hydrogen till the end, again, we're going to meet with equal success. What about L? What are we going to do last? Oxygen. We're certainly not going to do it first because it's in everything. So this is a combustion of sucrose, table sugar. Carbon first, hydrogen second, oxygen third, in virtually all organic compound combustions. 12 carbons, one place on the left and the right, 22 hydrogens, one place on the left and the right. Now we'll do oxygen, 11 and 24 is 35. 11 of those 35 are here, so we only need 24 more. So we're done. Exactly the same order works for this. This is combustion of ethanol. Carbon first, hydrogen second, oxygen third. 2 carbons, 6 hydrogens, 3 and 4 is 7 oxygens, one of them's here. So we only need 6 more, so again, it's embarrassing, it's so easy. What type of reaction is H? Think back to science 10.
It's the acid one.
Double replacement. Notice
It's the
in
acid,
terms of
but
Sherry's
it is a
hints,
double replacement thing. I wasn't
we've
even getting
got
that bad.
both sulfate and phosphate that stays together. So we're gonna balance those polyatomic ions as a unit. In the vast majority of double replacement reactions, particularly where there's polyatomic ions, pick the biggest compound and start by balancing the polyatomic ion in the biggest compound. So let's start by balancing phosphate in this thing. You got 2 phosphates on this side, you got 2 phosphates here. Then just go back and forth till you're done. 6 hydrogens here, 6 hydrogens there. 3 sulfate here, 3 sulfate there, 3 calcium there. Now, could you have taken the oxygen away from the phosphorus and the sulfur and balanced them individually? Sure. But unless you got a death wish, like, why do that? It's like it's way easier if they react together, balance them together. Let's pick a word equation. So on that page, there's a bunch of formula or skeletal equations. Let's pick a word equation here. And again, Sherry likes to scaffold her questions. Don't worry about the bouncing bonkers. Those are examples of reactions where you pretty much need a systematic, stepwise system. Those are all oxidation reduction reactions. They're if you take Chem 12 next year and I'm still teaching it, we'll talk about 2 methods to balance oxidation reduction reactions. Simple inspection is not going to do it for you. You might stumble on it by luck, but very difficult to balance these by inspection.
Oh yeah.
Let's pick H, because it looks like Sherry's given us a QR code there because she perceives it as being hard. So let's look at H, right? I don't know if that's typical of a test question, but see if we can use Sherry's hints to help us. Again, the key here is make sure the formulas are correct. Strong heating of copper 2 nitrate trihydrate. So that would be anhydrous copper 2 nitrate. But there's the hydrate. It's an ionic compound, so it's a solid at room temperature, and we heat it. Oftentimes, heat is represented as just a triangle. Okay, so we're heating it. Now look what we produce. We produce copper 2 oxide. It's a solid, as all ionic compounds are. We produce nitrogen dioxide, that's a gas. We produce oxygen gas. And we produce water, but it's correctly written, it's probably a gas because so much heat's produced that the water comes off as a vapor. So let's make sure we got everything. Copper 2 nitrate trihydrate produces copper 2 oxide, nitrogen dioxide, oxygen gas, and water. I'm gonna make that a little even level. Let's do 2 plus oxygen gas plus water. Now that looks a little intimidating, but I think we're safe in answering the first question. What are we not going to start by balancing?
Oxygen.
Oxygen. It's in everything. So let's not do oxygen. Copper's in one place on the left and the right. Nitrogen is in one place on the left and the right. Hydrogen is in one place on the left and the right. Everything is in one place on the left because there's only one reactor. So copper seems to be balanced. Now, it would be nice if nitrate stayed together as nitrate, but it doesn't. So we're gonna ignore the oxygen for now, we're gonna balance the nitrogen. On this side, we got 2 nitrogens. On this side, we only have 1. So that balances nitrogen. And again, we're gonna leave oxygen to the end. Then we go to hydrogen. We got 6 hydrogens over there. We only got 2 here, so we gotta put a 3 there. So the copper's balanced, the nitrogen's balanced, the hydrogen's balanced. Now we balance oxygen. So let's count oxygens on the left and the right.
6.
3 times 2 is 6. Plus 3, we got 9 oxygens over here.
5.
That compound has everything in it. Here we've got 1, and 4 is 5, 6, 7, 8, 9, 10. So how are we gonna get 1 more oxygen over here? The answer is we can't. Well, if we can't get 1 more oxygen over here, can we get 1 fewer oxygen over here?
Just drop the oxygen on copper.
How can we turn that into 1 oxygen? Can't lose that, but what can we do for a coefficient to turn this into 1?
Breathe one of
How?
them
Notice we're leaving the element till the end. Now, we can't leave it as a half, but right now it is balanced, isn't it? Now what do we do?
Times 2.
Multiply everything by 2. And it has to be balanced. 2 of all of those,
6.
2 of those, 4 of those, 1 of those, and 6 of these. Now that's, took a few steps, so this would be a really good example of now let's see how many of each element we actually have. So we got 2 copper, 2 copper. 2 times 2 is 4 nitrogen, so that's 4 nitrogen. We've got 3 times 2 is 6, times 2 is 12 hydrogens, or hydrogens. We've got 3 times 2 is 6, times 2 is 12, plus 3 is, well, 2 times 3, 6. So we've got 18. And we've got 9, and each times 2 is 18, so we've got 2, and 8 is 10, 12, 18. Okay.
But it's still written as O2.
Now, that's not all of them, but you kind of get the idea, okay? And you can be quite certain that when we do get to the end of chapter 4, which is a ways yet, there will be questions where you gotta write the formulas and you gotta balance it, okay? Now, I'm under no delusions that you guys are gonna work really hard at mastering this prior to Thursday, because Thursday is a review class, yes?
How come for the trihydrate, we didn't multiply it by 2?
Because that's the compound.
Oh, okay, so it's
Okay, so
one.
that's part of it.
Oh, okay.
In the same way, I couldn't just multiply this. So that thing is a fixed unit,
Okay.
yeah. So the review class is Thursday, and from the last review classes we've had, it's become clear to me that a bunch of people that didn't ask questions probably should have, or maybe had questions they were intending to ask but didn't. Let's get over that. It's a luxury you guys don't have. If there's a question you're wondering about, anything, ask it. Because there's probably other people wondering the same thing. And if everybody in here, if every person just had one question, rather than like 4 or 5 people having 6 or 7, I think the collective knowledge of the room would go up more than if, those same 4 or 5 people ask everything. Okay, got a question?
Oh yeah, will we get answer or questions like that wrong for no?
Is that typical for a test?
No, the how it changes, like added heat.
I wouldn't really, the only reason I put that in, cause Sherry put it at the top here. Write a balance formula equation, phase indicator should be included if possible. If I ask you to write states, I would give you enough information to include it, but in terms of the symbols, no, I wouldn't worry about that. Sometimes you'll see chemical species above and below the arrows, and whenever you see that, it means they're catalysts, or maybe the reaction conditions, right? But don't worry about that yet. So that's section 4.1. Review class is Thursday, test is Monday, and the makeup of the test is always already on Google Classroom. On Wednesday, the day after the test, it's very unlikely I'll have like 80 or 85 tests marked by Wednesday. So we'll probably press on into section 4.2, because as far as I'm concerned, obviously, you should practice these things, but it's easy to check your answers. But I will assume that we're moving on when we get to section 4.2 after the test. If you look at 4.2, the warm-up convinces you that, at least at some level, you've done this stuff before. So that's a review of the 6 reaction types we did in Science 10. But as I said, for each of these, there are extra information we're going to add in grade 11 that we didn't add in grade 10. We're not doing section 4.3. 4.3 is oxidation reduction. It's an interesting topic, it's just not part of the curriculum. If you're thinking about Chem 12 next year, it is a unit in Chem 12. After 4.3, we do, again, a bit of a review from what we did in Science 10. Remember last year we talked about exo and endothermic reactions, potential energy diagrams. We'll do that in section 4.4, although at a bit of a higher level. We'll actually quantify the energy changes. And then 4.5 and 4.6 are like the culmination of really everything we've done since the beginning of the year. It's stoichiometry, and it's all of the conversions, all of the formula writing and naming, all the mole calculations. All of that is kind of woven into 2 sections. And at the end of 4.6, that will finish, well, I'd like to say the first half of Chem 11, but it's going to be more than half the year. But the majority, the quantitative part of the course, the calculating part. What comes after that's going to be conceptual. Then we switch focuses and we go into atomic structure and a little bit of the history of our understanding of the atom and moving beyond the Bohr model, which was abandoned long ago, more than 100 years ago. And then we'll talk about quantum mechanics. But we're not going to get to that probably until sometime next month. So, homework for Thursday, review questions. If we run out of questions, which means you stop asking them, I'll probably press on in 4-2. Again, with the same understanding that none of that's gonna be on the test, but I would prefer that if we have the luxury of a full block on Thursday, that we should use as much of that as we can to solve any problems you have. Okay? Did any of you find this discussion on balancing helpful compared to last year? It's really not hard. It's really not hard. And don't look at an equation and think, if I can't balance it instantly, it's gonna be hard. Very few reactions can be balanced instantly. Just do it systematically. Okay? I'm not moving into 4-2 today, so with the 9 minutes or so you have left, or maybe a little more than 9, you can practice some of the questions in 4-1.